Bonjour, welcome back to QX01, an introduction to quantum information and its associated technologies. So let's have a look at the planning so far. So we've covered all these topics, and recently we had people from companies and research institutes to talk about quantum algorithms, quantum cryptography, and also quantum sensors. So today, I will give a lecture on quantum error correction, and then there will be two more lectures. One, so next week, given by the French company Atos, and they're going to introduce the so-called Atos quantum learning machine and what they can do with it. And then the last lectures will be given by a colleague from the University of Cartagena in Spain, and he's going to talk about various technologies to build a quantum computer, and in particular is going to focus on superconducting qubits and trapped ions. Right. So for today, these are the topics we're going to cover. So first of all, I'm going to talk about something I've talked about before, but really didn't get to, which is the fact that quantum physics tells you that you cannot clone a quantum state. Okay, so in fact, it's a very simple. There are two very simple proofs to show that a quantum state cannot be cloned. Okay, so you cannot make copies of a quantum state. And that's very important because this has to be taken into account for error correction, because I will then talk about what is error correction in a classical sense, and then I will show you that we can implement similar error correction schemes, but at the quantum level. And in particular, we'll focus on the so-called bit flip error. And then I will, of course, as usual, I will not be able to cover everything in the topic because it's very vast. So I will just finish by giving you some other types of errors that do exist and other types of codes. I'll give you an example, a couple of examples for the quantum error correction, but there are many others, like the Shor's 9-qubit code, for instance. And so on. And then I will finish by just giving you some results that have been obtained, physical results on quantum error correction, and more to the point, I will show you how important it is and how not easy it is. Right. So the no cloning theorem. The no-cloning theorem tells you that, as opposed to perhaps what one could do in biology, you could clone a sheep like Dolly. In quantum mechanics, there is no machine that will take as an input a quantum state and spit out the same quantum state and a perfect copy. Right? So there's no such machine. So we're going to show that. And so for that, we're going to assume that this machine, as we've seen before, can be modeled by a matrix, or an operator. It's a machine, it's an apparatus. So we have an operator. The only thing, as we've seen before, is this operator U, this cloning operator, whether it exists, has to be unitary. Okay, we have to. The rules is that this has to be unitary. So the question is, does this machine exist? And so this machine does not exist. So the proof number one is to use two states and the inner product for the first proof, and then there's a second proof afterward. So the no cloning theorem. So proof number one is that, so if you can have this machine, what it means is that I can take two states. So psi and phi. And I can always associate to this state a zero state, the vacuum state. Okay. And the idea is that using this machine, when I apply these machines through this operator U, this cloning operator, then I will make a copy of psi and phi onto this second ket, so onto this second bit of information if we talk about qubits. So then at the end I should get something like this, and like this. Okay. And so now, now what's interesting is to look at the inner product between the two and see that we will end up with some form of contradiction. So if I take the inner product, so phi psi, so I can always say that the psi and the phi is equal to that. So I can always say that this is equal to itself convoluted with the vacuum with nothing, with the zero state. And same for this one, except that this is the bra equivalent. So that means that I can always do this without losing any generality on my states and having basically the same result. And then what I can do is also say that in between here, I can insert the identity operator, and it won't change anything, right? But then the identity operator, I can write it as a function of this unitary transformation U. So U has to be unitary. And what does it mean? It means that U dagger U equals identity. So in other words, I can replace this identity that I inserted here by U dagger U. Okay? So if I do that, I'm going to have psi tensor product 0, U dagger U, and then 0 tensor product psi. And now I can apply the U dagger to the bra side, and I can apply the U operator to the ket side. And if I do that, well, I know that through this machine, this is going to give me psi, and is also going to give me phi. So I would have phi, so U dagger to the bra will give me phi, and then the other side I will have U applied to 0, which is going to give me psi, tensor product psi. Okay, so if I carry on, this is it. But then this tensor product is in fact the inner product squared. So in fact, I can rewrite this as in something like this. And that is what? That is phi psi squared. Okay. So in other words, I started with phi psi, and I end up with the inner product phi psi squared. So in other words, I have now the condition that x equals x squared. And that is only possible in two cases, if x equals 0 or x equals 1. Okay. So x equals 0 or x equals 1. So if x equals 0, that means that phi psi equals 0. So that means that these two states are orthogonal states. Okay. First of all, so that means phi psi. So phi psi phi are orthogonal. And then x equals 1 means that phi psi equals 1, and therefore psi equals phi. Okay. So in other words, in both cases, either so using the same cloning machine, either I end up by saying that basically I have the same state. So in fact, this is only possible, I can only clone these two states if they are the same. Well, yeah, makes sense. Or if these two are orthogonal, which means that they cannot be equal by definition because they are orthogonal. So in other words, this, through the inner product, yeah, this is okay. This and this are orthogonal. Means that there is no such machine that can realize this operation of cloning psi and phi at the same time. So that's proof number 1. And proof number 2 is even easier to understand, is to use the linearity of quantum mechanics. And in fact, this was the original proof. So I will get rid of that. So proof number 2, through linearity, tells you that, okay, so I start with psi, and I want to clone it through this machine, so through this hypothetical unitary transformation U. So this machine should give me this result. Okay. If I assume that the psi is a qubit of the form A0 plus B1, most general qubit we've seen before, that means that this will give me A0 plus B1 tensor product A0 plus B1. So that will give me 4 states. We've seen them before. So give me A squared 0, 0 plus AB 0, 1 plus B A 1, 0 plus B squared 1, 1. Okay, so that's one hand. And on the other hand, if I start with this state, then that means that I want to clone this state. So I want to, so with the tensor product with 0. So if I want to clone that state, that means that I should be able to say that this is, this should give me 0, 0 and 1, 0. But through this cloning machine, so this should give me A 0, 0 plus B 1, 0. This is what it is. But through the cloning machine, that for this qubit and this qubit, I have to have the same state on this qubit. So that this should be 0, that's the case, and this should be 1 to match this 1 qubit. So that means that this machine is going to do something like transforming psi into A 0, 0 plus B 1, 1. Because by doing so, what we did is we linearly clone this state and clone this one. And the sum is the linear sum, so it's the sum of the two. Okay? So what it means here is that through these two, so on one hand, the cloning machine does this and gives us this result. On the other hand, the cloning machine, the same cloning machine, is supposed to also do this. It's just another view of seeing it. And clearly, this and this are not equal. Okay? Here you have the 4 terms, and then even the coefficients are not the same. Okay? So this does not exist. So there is no such thing as a cloning machine for quantum states. Okay? And that's, again, is a very important property, and it's a property that is at the heart of, one of the properties at the heart of quantum technologies, and in particular, at the heart of quantum communications and quantum cryptography, as we've seen before. Right. Okay. So let's start for the no cloning theorem. And because the idea is I'm going to use that property for the quantum error correction and to show how we cannot just translate quantum error correction, classical error correction, to quantum error correction. Although it does work as well, we can find out schemes to quantum error correct an algorithm. Right, so before talking about quantum error correction, let's talk about classical error correction. So error correction is known in the classical world. So here we're going to assume only one, the sort of simplest error possible, which is a bit flip error. So what it means is that you have a string of numbers, 0, 0, 1, 1, 0, 0 of bits of information, and then at some point, so you transmit that, so this is what you transmit, and then it goes into a channel, and then somehow your colleague gets on the other side gets the result, but somehow it doesn't get exactly the same thing because some error, some noise, bit flip, this one, for instance, from 1 to 0. Okay? So in some cases it doesn't matter, it's fine, but in some cases it does matter. So you want to find a way, in fact you want two things. You want first to be able to detect that there is error, because you would be able to tell. If I send you a bit of string, unless you actually call the person who sent it to you and say, what did you send me again? And compare and waste a lot of time, and you have no idea whether there's a mistake. Okay, so first of all, you want to be able to detect the mistake. And second of all, you would like to correct it if possible. And so error correction, there are schemes to do that. So the first scheme is detecting it. And for that, and so a bit flip error means that you go from 0 to 1 or 1 to 0, just to make sure. And so this sort of simplest error, the bit flip error, is what we call the, or this scheme is what we call the binary symmetric channel. And there are a few assumptions, which are fair assumptions. The first assumption is that we assume that errors are not related to each other. Okay, so what it means is that when you send this information into the wild and is recovered on the other side, there will be errors, there will be noise, but it's not, so if there is a mistake here, there could be a mistake in another one later on, but they're not related. Okay, it's purely random that sometimes this one gets an error and the other one after gets an error. So there is no relation with each other, which again seems to be a fair assumption. You also assume that the probability of occurring is very small. Okay, because if it's too high, then well, you might as well not do anything. So you have to assume some form of the fact that sometimes you have an error, but not too often. Okay? Which means that basically in this case you have to worry after 1 over p iteration, but that we assume that this is the case. So we do have the errors occurring. So we would like to detect them and then to correct them. So how do you get around this? So one way of getting around it, or at least detecting it, is to add what we call, to do what's called redundant coding. And by making multiple copies. And in this case, for detecting, you only need to make 1 copy. Okay? So what it means is that for each bit of information, you double it. Okay? So each time you have a 0, you code it as a 0, 0. And each time you have a 1, you code it as a 1, 1. Okay? And so if you do that, and if you have a probability p of having an error, that means you can go from 0 to 1 with the probability p, or you can go from 1 to 0 with the probability p, or you can remain from 0 to 0 and 1 to 1 with the probability 1 minus p, again with p being much smaller than 1. Okay. So the good thing is that, in fact, this is very easy because if we have a mistake, if we have an error, that means we go from 0, 0 or 1, 1 to 0, 1 or 1, 0. Okay? And so let's write that down. So if you go from, so you send for each qubit, for each bit, sorry, of information, you send 2 of them. So you made 1 copies and you send the two copies together, the original and the copy. So 0 becomes 0, 0, and 1 becomes 1, 1. Okay. And so each of those, okay, so it means that at the end, there are 4 possibilities. Either you get 0, 0, 1, 1, then you don't have to worry. That means there is no error. Or one of them is flipped, say this one, so you get 0, 1. Or the other one is flipped, say this one, and you get 1, 0. And it's because then what you do is for each of them you check the parity. So you sum them. So this parity would be the same. That will be an even parity. 0 plus 0, 0, 1 plus 1, 0. Same parity. But if you have one of these two results, you will get an odd parity. Right? So you get 0 plus 1, 1, or 1 plus 0, 1. So very easy. So what you need to do is to sum the two. If you've got an even, there is no mistake. If you get an odd parity, there's a mistake. Okay, so no error. Error.
Once we know that there is an error, how do we define which one of the 2 bits contains the error?
So this scheme is a 2-qubit scheme. It only tells you that there is an error. It doesn't tell you where, and it doesn't tell you how to correct it. So if you want to go further, you do need, which we're about to do, you do need to make yet another copy. So it's a 3-bit encoding, and that will tell you which one has an error, so that you can correct it. But it's at this stage, that's what I said, you can only detect there's an error. That's all you can do. Okay, first step. And again, I insist that you don't need to know what you started with. Huh? All you need to know is that if you have an even parity, then you're fine. If you don't, then you're not fine. So now, indeed, if you want to correct that, there is a slight mistake here, but oops, by the way. Here it should be 1, 0, and there is an extra 0. So if you want to correct now, you need to do more. So you need a 3-qubit encoding. Okay. So now, so this is the 2-bit encoding, so not qubit, bit encoding, 2-bit encoding. That's to detect errors. Okay. With a 3-bit encoding, as we will see, we'll be able to tell you which one is a mistake and therefore how to correct it. 3-bit encoding is that correct errors. So now you need to have 3 copies. So you go from 0 to 0, 0, 0, and you go from 1 to 1, 1, 1. So if you have a bit flip on one of those, so again, it means that for each of these, so this one should be 0, 0, 0. This one should be 0, 0, 0. This one should be 1, 1, 1, etc., etc. And now, if you have a bit flip, then you have 6 possibilities, right? So if 1 bit flip, then you have 6 possibilities. Okay? 3 on this one and 3 on this one. Okay, so this one, so 2 families, so you've got 0, 0, 1, or 0, 1, 0, or 1, 0, 0. Okay? And then this one, also 3 possibilities of bit flip, which is 1, 1, 0, 1, 1, 0, or 1, 0, 1, or 0, 1, 1. Okay? And so already, now what you can do is do what is so-called the majority rule. So majority rule is that for whatever state you have, whatever string you have, is you add them up. So if you add them up, okay, so the majority rule which is simply adding them, more like earlier, in fact. This one will give you 1, this one will give you 1, this one will give you 1. So all of them will give you 1. But these 3, this one will give you 1 plus 1, so 0. This one will be 0, and this one will be 0. So in other words, by adding them, you know if the mistake on here or if the mistake was on here. That's nice. But you can even, you still don't know because you still have 3 possibilities. So it could be this error or this error or this error. That you don't know. You know it's one of these 3 because you did the majority rule, or it's one of these 3 because you did the majority rule, but you don't know if it's one of these 3 or one of these 3. Okay? So you need something else, and what you do is you do the next step, which is now to check the parity of 2 bits, of bits 1 and 2, and bits 2 and 3. Okay? So if I have, so let's write down these six ones. So 0, 0, 0 gave us 0, 0, 1, 0, 1, 0, and 1, 0, 0. Okay? And then 1, 1, 1 gave us 1, 1, 0, 1, 0, 1, and 0, 1, 1. Okay? So that's, so we have, so this one is bit 1. This one is bit 2. And this one is bit 3. And so now you do the parity check for 1 and 2, and 2 and 3. So then you will end up with 2 bits, one for the parity of 1 and 2, and one for the parity of 2 and 3. Right? So here we have 3 possibilities. So we've got, 0, 0 will give us 0, and 0, 1 will give us 1. 0, 1 will give us 1, 1, 0 will give us 1. And then 1, 0 will give us 1, and 0, 0 will give us 0. Then in this case, we have 1, 1 give us 0, and 1, 0 give us 1. This one will give us 1, this one 1, this one 1, and this one 0. Okay. And of course, I forgot the case. I should add it. Is these 2 cases when you have no mistake. Okay. So if you do the parity check on these, then you end up with 0, 0, 0, 0, 0, 0, and then 1, 1, 0, and then 1, 1, 0. So we can see here that when there is no mistake, we always end up with a parity check of 0, 0 for 1, 2, and 2, 3. So if we have this, then no worries. Okay? There's no problem. There's no mistake. Good. But now if we get one of those possibility, then there's a mistake. Except that now, if I get 0, 1, and 0, 1, what I can say in these occurrences is that, so it corresponds to this one is this one. What you can see is that it means that the bit 3 has flipped, right? Because you started from 0, 0, 0, you end up with 0, 0, 1, or you started from 1, 1, 1, and you end up with 1, 1, 0. So in both cases, it's bit 3 that flipped. Okay? So that's bit 3 flip. And that's the same here, bit 3 flip. Now when I've got 1, 0, 1, 0, and 1, 0, you can see it corresponds to this one and this one. And in this case is bit 1 that has flipped, because you went from 0, 0, 0 to 1, 0, 0, or from 1, 1, 1 to 0, 1, 1. So in both cases, it's the bit 1 that flipped. So this one corresponds to bit 1 flip. Bit 1 flip. And the last case will be a bit 2 flip. Indeed it is, because I've got 1, 1, and 1, 1. That means what? 1, 1, and 1, 1 means that I went from 0, 1, 0 or 1, 0, 1. So in both cases, it's the bit 2 that flipped. Okay? Okay. So you could say, okay, but we have a problem because I don't know. I know it's bit 2 that flipped, but I don't know if it comes from 0, 0, 0 or if it comes from 1, 1, 1. It doesn't tell you that. But yes, you do know that, because we knew from here, from the majority rule, that the mistake was either on this guy or on this guy. So when you add this, you go here, and then you know which bit, 1, 2, or 3. Or the majority rules tells you that you go from here to these cases, and so these 3 possibilities of parity check, and therefore, whether it's bit 3, 2, or 1. Okay. So by doing this, So when you have the majority check, so when you have the parity bits of 1, 2, and 2, 3 plus the majority check, then you have a unique answer. Okay, that is, I know which bit has been flipped, so I can just change it. So that works, but only works if you have a single bit flip.
I'm wondering why we need the majority check. Because with the parity rule, we can find out which bit flipped. Then if we just flip the bit that we determine, we can obtain the original signal. For example, with 0, 0, 1, if we do the parity check, we obtain 0, 1. We know that the bit 3 flipped, and then we can just flip again the bit 3 to obtain the original signal.
Yeah, yeah, it's true that it's true that with this only you can just say, well, I can just flip it. I don't know which one I have, but I know that the mistake is on bit 3, so I can just flip it. So it's true. I guess it depends on how. I suppose it depends on. So I would assume that when people do error correction, before flipping it, they want to know if there's an error. That's all. But you're right. Otherwise, I think it's well, not think. It's for sure. It's more costly to do that than to do that. So I guess that's the reason why. Is you would like, but yeah, it's a fair point. You would like to know first whether you have a mistake, and if you do, then how to correct it. But it's true. You can also say, I don't need that. I want to make sure I don't have a mistake, so I go directly into the parity check of 1, 2, and 2, 3. It's true. So I guess it depends. I think it depends on the cases and depends on the applications. But it's true. You don't necessarily need the two at the same time. What is true, though, is that this is all very well, but it's only very well for a single bit flip. So if you have 2-bit flip or 3-bit flips, then this doesn't work anymore. But the idea is that, so if you have, so this is okay for a single bit flip. Okay. So, but not for 2 or 3. Okay, so what it means, 2-bit flip means you go from, say, 0, 0 to 0, 1, 1, or 1, 0, 1, or 1, 1, 0. Okay? And a 3-bit flip means that you go from 0, 0, 0 to 1, 1, 1. Okay? And that already, the majority rule, for instance, won't help you if you have a 3-bit flip. Because you say, oh, there's no mistake. But in fact, there is. There is triple mistake. So in other words, it means that so what is the lower limit? Well, the lower limit, as you can see here, is that it's basically the probability of having 3. So that's only one. There's only one possibility when you bit flip the 3 of them. So it would be with the probability p to the cube. Okay, so p times p times p, because for each qubit you have a p probability of flipping, we said. Okay, plus 3 times, because you have 3 possibilities of bit flipping 2 qubits. So plus 3 of bit flipping 2 qubits, that would be p squared, because every time you split a bit of information, you have probability p. So that's one flip and another flip, times 1 minus p of non-flipping. So that would be, in this case, it would be this one, and this one. Okay, so this occurs with probability p, and then 1 minus p. Okay. So in other words, that means that this is very well as long as p is bigger than all of this. Okay. And that's the case. So you have an example here, is that if your probability is 10%, which is quite a lot, actually. When I remember I said this works for p much smaller than 1, so it's probably on the order of 1% rather. But even 10%, this quantity is on the order of 3%. Okay. So it's and of course, if p goes down, then as you have cube in square, this will go down even more. But, so this classical error correction works with some certain limit. There can be more complex ones where you can increase, you can take into account the fact that you have several bit flips, but of course that would have a cost in terms of number of bits that you want to use. But the fact is that you can go from this level of error, say 10%, down to 3% using this scheme. So it's worth doing classical error correction. It's possible. Okay. So that's that. Now the question is, can we do the same with the quantum bits, qubits? So the answer is yes and no. Okay. Yes, in the sense that yes, we can quantum error correct qubits, and no, in the sense that we cannot use the same techniques because, well, we cannot clone. So I cannot just take 0 and make it a 0, 0. We just showed that there's no cloning machine that can do that. Okay. So let's have a look at let's have a further look at that. So we have indeed several issues where we cannot just translate the classical error correction to the quantum one. The first one, the main one, is that we cannot make copies. Okay, so that's a biggie. But it's not the only one. Okay, so let me get rid of this. So the first issue is that the no cloning theorem forbids making copies of any quantum states. Therefore, I cannot make these multiple copies. Okay. The second problem we have, as we've seen before, is that the measurement destroys the quantum state. So I cannot just measure my quantum state and see whether I have a mistake and then correct it, because I've destroyed it. I've changed it by measuring it. So I cannot do that. And the third problem, which is by far not the biggest problem compared to the other two, is on top of it, we are dealing with continuous states, right? We can go, because the quantum state, a qubit, is a superposition of 0 and 1 in a continuum of coefficients a, b, or alpha, beta, as opposed to a single bit, which is 0 or 1, and that's it. There is no half a 0 or half a 1. It's just either 0 or 1. So this is a problem. And yet we will see that using the same tools as before, entanglement and superposition, we will be able to do a quantum error correction code. Just a side note is that we've seen the importance of the Pauli matrices, where is an example here, is that if I'm interested in again, just a bit flip operation, a bit flip error, then the bit flip error in this case is simply applying an X gate, right? Because an X gate is flipping 0 and 1 and 1 and 0. So basically, an error, a bit flip error in the quantum world is I have my state, I send it into the world, I've got noise, and I end up with this state. So what the noise did is actually did a X gate Pauli matrix. Okay, so that's good. Because it means there's an easy way to encode this bit flip operation. That's good news. So how are we going to do this? Well, we're still going to use a similar idea, that like in the case of the 3-bit code, we are going to protect a qubit by embedding it in a 3-qubit state. There are other schemes, the 5, 7, 9. We won't see all of them, but we'll have a look at the 3-qubit state. So how do we do this? So the idea is that we want to go from this state, which in the most general case will be the qubit alpha 0 plus beta 1. And we want to protect it, to embed it into a 3-qubit state. So that means we need to add 2 others, which will be initially in the 0 state. And then what we want is to end up with a state that will be alpha 0, 0, 0 plus beta 1, 1, 1. Okay. So again, we have our 0 and our 1 here. But then now we added the 2 extra qubits, 2 and 3, to embed it in a 3-qubit state. Okay. And this, by the way, this particular state is called a GHZ state for Greenberger-Horn-Zeilinger state. And as we will see, is a particular state that is used in quantum technologies in different schemes, and one of them being to do error correction. So the question is, how do I go from this to that? Okay, first of all, is this even possible? So the answer is yes, it's possible. And you've got the equivalent circuit there. So let's have a look at that. So I start from 3 qubits, okay, 0, 0, 0, knowing that this is the one that is of interest. And first, I'm going to apply a Hadamard gate to make it in a superposition state. Okay. So at this stage, basically, I'm here. Okay. And then what I'm going to do in order to create this state is I'm going to use a CNOT gate twice between this guy and this one first, and this guy and this one after. Okay. So I'm going to apply a CNOT gate between 1 and 2, and then between 1 and 3. Okay. So here you have the different times. You have to read that this is done in time. You apply the Hadamard gate, and then the C0 1, and then C0 2. Okay, and you look. So if I look at time t0, as we see here, t0 I have the state 0, 0, 0, or the state we've seen before, tensor product 0, 0, 0. Same thing. Then at time t1, then I applied Hadamard gate on qubit 1 only. So I end up with superpositioning of this one. And that will give me, so in this case of a Hadamard gate, 1 square root of 2. It doesn't have to be. I can keep alpha beta, but let's play with this. In fact, let's keep this. Yeah, we can, doesn't matter. So it would be 1/2 of 0, 0, 0 plus 1, 0, 0. Okay. And then at time 2, that's the time before the second C0 and after the first C0 gate, between 1 and 2. So that means I apply the C0 gate between 1 and 2, so between this one and this one. And I end up with 0, 0, 0 plus 1, 1, 0. The CNOT gate is basically on the first qubit do nothing, and on the second one you flip it. Okay. As an exercise, so just take the state 0, 0. So this can be written as in 0, 0 plus 1, 0, 0. And you apply the CNOT gate between the two. And you will end up with 0, 0 plus 1, 1. So yeah, that's a good exercise. And then at time t3 is after applying the second CNOT gate, but this time between 1 and 3. So you'll end up with the same as here. So what we've done is we took these two and we CNOTed to get this one flipped. And now we take these two and we CNOTed to get this one flipped. So now we will go from 0, 0, 0, 0, 0, 0, 1, 0 to 1, 1, 1. Okay? So after T3, we have 1 over the square root of 2, and we have 0, 0, 0 plus 1, 1, 1, which is this so-called GHZ state that we want. Okay? So, okay, so this is the encoding the original qubit into now a GHZ state, a 3 qubit state. And by the way, we did not make a copy. This is not a copy of that. We demonstrated earlier. A copy of that would look like this, because we cannot. Okay, so if we have a bit flip error, then we have 3 cases only. Okay, because if this bit flips, that means this is 1, but this one has to be 0 because it's the same qubit, right? I mean, if I go back here, remember, a bit flip in quantum world means that for this qubit, 0 is replaced by 1 and 1 is replaced by 0. Okay? So a bit flip can only occur onto this family, or this family. So we would have only, so bit flip or qubit flip would be either 1, 0, 0, plus 0, 1, 1, or 0, 1, 0, and then this one bit flipped, so plus 1, 0, 1. Or this one has been flipped, that means 0, 0, 1, plus 1, 1, 0. Okay, so we have only 3 possibilities. And so again, like in the classical case, I can do a parity check on 1 and 2 and 2 and 3, and that will tell us which error it is, okay, which qubit has an error. So if I do a parity check, so if I've got, so parity check on that will be 1, 0, and so that would be 1, and then that would be 0, then that would be 1, that would be 0, so it's the same one, okay? This one will give us 1 in both cases, because I would have 0, 1 and 0, 1. Okay, so let's do it. So here we would have, the parity check would be 1, 0 for both of them, this one and this one, and this one and this one. Here for both cases is going to give me 0, 1 and 1, 0, or 1, 0 and 0, 1, so it's going to give me 0, 1, or 1, 0 actually. And this one is going to give me 0 or 1, 0 and 1, sorry, or 0 and 0. Okay. So we basically have 3 different cases, which means that the parity check will be able to tell us on which of the 3 possibilities the error has occurred. Now the question is, how do we correct it? And that's where it's becoming a bit more complicated. So let's have a look at this circuit. So here we have the original qubit that we want to correct. That's qubit number 1, that's this one. And these are the 2 qubits that we're going to add to this one to encode it in a 3-qubit state, in a GHZ state. So for that, we do this operation here that we just seen. So MR, or if we directly from this, we just C0 1 and 2 and C0 2 and 3. And then it goes into a noisy channel, and we end up with a state, psi1, that will have 4 possibilities. So either it's going to give us 0, 0, 0 plus 1, 1, 1, that means it hasn't been touched, or, well, like the 3 that are there, so 1, 0, 0 plus this one, and this one. And then what you do is, and that's where error correction starts to be different than, really different than classical error correction, is that you need extra qubits that we call Ancillar Qubits. And you need them because you need them to be able to check the parity. And in order to do that, and you do that because you need to make measurements somewhere. And you can't make measurements here, because if you make measurement on this state, then you change it. You don't want to change it, you want to keep it. In fact, you want to correct it. So that means that you need to do, but we need to do a parity check. So in order to do a parity check, we need to measure something. We need to know, whether we've got the sum gives us a 1 or a 0. So that's why we need 2 extra qubits, 1 to do the parity check on 1 and 2, and 1 to do the parity check on 2 and 3. So that's why you have these 2 extra qubits, which we call Ancillar Qubits, here and there. And then you do the parity check, so that's the M1. M1. So where is the 3? Okay, sorry. So you do the 2 parity check on 1 and 2 and 2 and 3, sorry, for each of them, because you need to measure 2 parity checks. You need to have 2 results. You need to do the parity check for this pair, the parity check for this pair. So hence the two ancillars. And then how you do that is that each of these ancilla will be itself sorted with the previous 3. Okay? And then you make a measurement of this one. This one you do measure. It's okay because you use it. You basically, so C0 it means that you entangled it with your system, and then you measure it. And by entangling it with your system, and then measure it, you can tell whether the original state was in one of these 3. That's the idea. Okay. And so you do M1 and then M2, and then you do the check. So either you find 0, 0, that means, well, there is no error, basically. The parity check is always 0, 0, 0, 0, 0. Or you find 1, 0. Or you find, this was a mistake here, sorry. 1, 1. Yeah, I knew there was something wrong here. Because in both cases, you have a 1. Here and here, so you get a 1, 1, sorry. Or you get a 0, 1, because there's always a 0 and a 1. Okay, so 0, 1, 0, 1. So you always end up with 0, 1. And so here we go. That means that by measuring, depending on the result you have here for Ancillar, and this Ancillar, then you know in which of the 4 cases you are. Either you are in cases where there is no error, so you don't do anything, or you're in the case 1 where the error was made on the qubit 1, qubit 2, or qubit 3. Okay? And you can tell by the combination of these two, if you get 0 and 0, then you do nothing. If you get 1 and 0, then you have to do something on qubit 1. If you have 0 and 1, then you have to do something on qubit 3. Sorry, on qubit 3. And if you have 1 and 1, that means you have to do something on qubit number 2. Okay? And so this you feed back into your 3 qubits that you have not measured. You have not measured them. What you've measured is the Ancillar qubits that you entangled during the travel, so to say. And then you do this so-called recovery stage. The recovery stage means that you need to do something in order to change the error, to bit flip back the qubit that has been bit flipped. So for that, if you find 1 and 0, that means qubit 1 was flipped. So what you do is you apply, well, we know we apply the X gate, because the X gate flips the qubit, so you will flip it back. Okay? If it has been flipped on qubit 2, then what you do is you apply identity to 1, so you do nothing. Qubit flip number 2 and do nothing to the third one. So that this would be qubit flip, so 1 will be replaced by 0, and 0 will be replaced by 1, and you end up yet again with this state. And likewise here, you qubit flip number 3, so that means in terms of tensor product, you remember when if you want to apply different single qubit operators on 3 qubit, for instance, that means you do the tensor product of the 3 different operators on each of these qubits. Except that here, 2 of these operators are just identity operators because you're not supposed to touch this one and this one because they haven't been touched in this particular case. But the third one here has to be bit flipped. Okay? So that would be the recovery stage, and then afterwards you end up with the psi2 state, which in all cases will be the one that you started with. Okay? So, in other words, so you can do error correction on quantum states, but as you can see, it comes with big overheads. The big overheads is that it comes with the fact that, first of all, you start from 1 qubit. You need to kind of protect it by adding 2 more. That's already something. And then you need to make indirect measurements, because you can't make direct measurements, indirect measurements on 2 qubits that you will sacrifice, basically. And these are the so-called Ancillar qubits that you add to your system that you will measure and throw away, basically, in order to go to the recovery stage and then end up with the state you started with. So de facto here, even though it's a 3-qubit encoding, you actually need 5 qubits to do that. 3 encoding ones and 2 ancillars. So that's a massive problem, and that's the big difference with classical error correction, is that quantum error correction, well, at least the good news is it's possible, but the bad news is that it requires a lot more resources, a lot more qubits. But at least it does exist. Okay. Now, there are other types of errors, because so what we just talked about so far is the bit flip error. But there is also the phase flip error. Okay, remember that this state is a qubit state, but this state is also a qubit state. It's just a different one with a different phase. Okay. And so you can, if you send this qubit into the wild, you can have an error which is either it bit flips or a phase occurs. For instance, if you remember, we talked about photons as being a good qubit in the polarization state of a photon. Well, it's very easy for it to get a phase. Put it in an optical fiber. The optical fiber will twist. It will be twisted, and the polarization state will be twisted inside, and so you will end up at the end with an extra phase on your light, and therefore on your photon, and therefore on your qubit. So it's very easy to do that. Okay? In other systems, the phase might not be so easy, but the bit flip will be easier. Depends on your system. And some systems, you can have a bit flip and a phase flip. You can have both of them, like so. So you can go from the identity matrix, where you don't do anything, the state hasn't changed, to bit flipping, to phase flipping, or to bit and phase flipping. And again, at least the good news is that each of these errors that we haven't talked about so far, we only dealt with the bit flip error, so that you can tell, by the way, depending on your system, you know in advance what is the most likely error that you can have, whether it's a bit flip, majority will be a bit flip, or phase flip, or both of them. Okay. But the fact is, this is most general, and the good news is that each of these errors, so bit flip, we already said, can be represented by an X gate, X Pauli matrix. The phase flip is basically the Z Pauli matrix, and the bit and phase is the Y Pauli matrix, which can be written as a combination of X and Z, as we've seen before. Okay. So those are the other type of errors that may occur, and therefore that means you need schemes to be able to correct them. So speaking of extra schemes, so here is the so-called 9-qubit Shor code. Okay, so the 9-qubit Shor code is a bit more complicated than what we just did, because as you can see here, you start with your qubit, and rather than having 2 extra protecting qubits, then you have 8 more of them. So that at the end you get a 9-qubit encoding. And you can see, so we're not going through, so what you do first is that you will do, it's a similar operation, is that you take your state and you entangle it with some families of qubits. So here would be with number 4, and then with number 6. Then you do Hadamard gate, and then you entangle it, entangle these 2 together, so with 2 and 3, and then you also do with 4 and 6. 1, 2, 3, 4, and 6, yes, and then with 7 with 8 and 9. Okay. But by doing so, because you've entangled this one and this one and this one and this one, and then by proximity, you basically have an entire 9-qubit encoding state. Then it goes to the environment. This is where, whatever things can happen. So it could be nothing, or a bit flip, or phase flip, or both of them. And then no matter what happened there, then what you can do is by applying, sort of reversing this. So you can see more C-node gates, and then C-node over C-node. between these three and these three and these three, basically you end up at the end, you manage to correct, so each of these operations will correct any mistake, any error that can occur, whether it's, again, a bit flip, a phase flip, or a bit in phase. And so at the end, you recoup, no matter what happened here, in this E stands for environment, no matter what happened there, the at the end, the psi state would be the one that you sent it in the first place. But again, you can see here that, so to correct a bit flip, we needed 5, in total, 4 extra qubits, 2 ancillars and 2 encoding. And for the Shor algorithms, you don't need ancillars, but you need a lot more extra qubits. You need 8 of them. The good news is that this can correct any mistake, any error. But still, that means for each qubit, you actually need 9 qubits. Okay. So that's why there are some major concerns, true concerns, onto how we can implement that, because the cost of having to do technologically to increase the number of qubits is not something that can be done easily. Okay. But anyway, again, like I said, this is the good news, which was not clear at the beginning, is that there are ways of correcting quantum errors, okay, which at the beginning seemed quite unlikely because there's no copy to be done. And in fact, there are more, there are other codes. This one I'm not going to even pretend to go through, but just for that you know that there are actually classes of codes, the so-called CSS codes for Calder-Bank, Shor, and Steen classes of codes, which have other names called stabilizer codes. And the stabilizer codes, you have an example here of a 5-qubit stabilizer, is that no matter what happened to the qubit using these classes of stabilizers, of codes, you will recover the qubit that you have in the first place. Okay. There are different types of stabilizers. So some of them, so this one, for instance, is a 5-qubit one, so that means it's less costly than the Shor 9-qubit code. Okay, but in this case, what you need to do though is that you need to, to have, so stabilizers means that basically you're going to have a lot of single qubit operation. X and Z and identity and X and Z and X and Z and X and Z and X and Z. And that's because what you're going to do in a way is that you're going to mix and mix and mix these states or these corrupted states until at the end you will find a combination so that at the end you have the right state that you started with. So it's less costly in terms of qubits, but it's more costly in terms of gates that you have to do. So it depends on your system whether you want to, whether you can afford more qubits or whether you can afford more gates. Okay. Right. So the last part is implementation of quantum error corrections. And so perhaps before I do this, as I have some time, I can quickly come back to that, where I was a bit quick earlier, just so that we understand how we can basically go from a single qubit state like this and then encode it into, in this case, a 3-qubit state. Because the whole key point, whether you use the stabilizer codes or the Shor or any of those, or this one, is that you need to be able to encode your single qubit into 3, 5, 7, 9 qubit state. So these operations here are very important. So the C-knotting of your qubit with others is important. So I just want to quickly come back, as I have some time, onto this step here. So if I go back, so we started with the state that is of interest, and we first applied the Hadamard gates. Okay, so we go from this one, which is 0, 0, 0, to 1/2 of 0, 0. Sorry, it should even be. Well, this is fine, but actually this is much better. So it's a good thing I went back to it. Because I've got 0, 0 here and 0, 0 here, because this is qubit 2 and 3, and they haven't been touched, right? So far up to this stage, this qubit and this qubit have not been touched. Only this one has been touched. So I've got superpositioning of the first qubit, okay? And then I apply a C0 between 1 and 2, okay? So if we recall the C0 gate is a 2-qubit gate, and it's 1, 0, 0, 0, 0, 1, 0. And we have, in this corner, we have the identity. And then we have lots of zeros, and then here we have the diagonal, so the bit flip, which is 0, 1, 1, 0. Okay, so this is the 4x4 2-qubit state matrix, or 2-qubit gate. So now I apply this to 1 and 2. So 1 and 2, if I rewrite this, will be, which is what I wrote originally, 1 square root of 2 of 0, 0, plus 1, 0, and then qubit 3, which I do not touch at this stage. Okay, this one is left untouched. So now that means I have to apply the C0 gate to this state. And this state, if you remember, we write this is a 2-qubit state. If you remember, a 2-qubit state is basically 0, 0, 0, 1, 1, 0, and 1, 1. Okay? So in this case, that means I have the vector 1 square root of 2 of 0, 0, and 1, 0. So that means I have to apply this to here times square root of 2. Okay, so this would be the equivalent of that. Okay, so that's so I'm going to end up with the 4 vector. So I've got 1 and then 1, then I've got 0, then I've got 0, and then I've got 0, 0, 1, 0, 0, 1, 0, 1, 0, so I've got 1 here. Okay. So what I have now is the state, and then 1 square root of 2. It's the state 1 square root of 2 of 0, 0, plus 1, 1. Okay. That's for qubit 1 and 2, so here. And then I need to add qubit 3, so I've got also this. Okay. So now at this stage, up to here, I've got this now, right? Because I've got 0, 0, 0, plus 1, 1, 0. Okay, so this. Okay. So almost there. Almost there, we want that. So for that, what I do is I do, again, a C0, but this time between 1 and 3. Okay? So if I do a C0 between 1 and 3, so let's go here. So 1 and 3 now is what? Is this one and this one, so it's 0, 0, and 1, 0. So 0, 0, and 1, 0 is yet again this state. so I've got 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. And then I apply it onto 1, 0, 1, 0. So I will end up with the same result, which is 1, 0, 0, 1. Except that now, so that's 0, 0 plus 1, 1, except that now this is qubit 1 and this is qubit 3. Okay? So I need to insert qubit 2 in the middle, which is a 0 and a 1. Okay? So after this operation at time 3, I end up with the state that I wanted, which is 1 squared of 2 of 0, 0, 0 plus 1, 1, 1. Okay? So I started with that. The first synod basically flipped this one, and the second synod flipped this one. And I end up with this, which is again what we call these so-called GHZ states. Okay. So this is important, but if you remember also when we talked about the quantum gates, we said that there are many quantum gates, but actually, you only need a few in order to do universal quantum computing or universal information. And in fact, this is another illustration of the fact that with the CNOT gate, you can go from this simple qubit to a much more complex 3-qubit state. Okay. But of course, the real problem is to actually implement CNOT gates, and that's not so easy. Okay, so in real life, CNOT gates are not easily done. Anyway, so to finish, just a word on the implementation of quantum error corrections. So I gave you here 3 examples, but there aren't that many more. In fact, there's only one more in terms of system, which is superconducting qubits, which is not here. But otherwise, that's it. It has not been implemented in other type of systems. So the first time it was implemented was in 1998, and it was done on the nuclear magnetic resonance system. So it's something that people have stopped using because it's not really scalable. So after 2 or 3 qubits, you couldn't do more. But nevertheless, they managed to. So they use this molecule, which is simply the trichloroethylene, where you have 2 carbons, and each of these carbons is basically, so the nuclear spin. The nuclear spin of carbon 1 and carbon 2. So this would be qubit 1, and this would be qubit 2. Okay. And basically by NMR, you can manipulate these qubits, and you can make a CNOT gate or just manipulate one of them only. So that's why it was very easy to do that. That's why people used to work with these systems at the beginning, because it was very easily done to manipulate 2, 3, up to 4 qubits. Okay, but this was limited to that. But the fact is, you could do that, and what they've managed in this first experimental quantum error correction is to show that when you have no error correction scheme, you get, so this is F is the fidelity of whatever state you wanted, so the fidelity of this state, how you preserve it in time. And of course, we're talking about nuclear spins, so these nuclear spins so they will be in a qubit state, exactly like the electron spin, and it's the same idea as a spin. It's just a spin of the nucleus rather than a spin of the electron. So you can put it in a superposition state, but this superposition state of a qubit will not remain in time. So after some time, it will decay. So the fidelity of your state will decrease. And you can see that you can go from quite high fidelity up to 90% fidelity down to 50% after a second of interaction. But what they've showed is that if you implement a quantum error code, so by adding, so in this case what they've done actually is they use a single qubit and they use the other one as the 2-qubit corrector. So they didn't use a 3-state, they use a 2-state. But they use a similar scheme, and what they found is that they can increase the fidelity from 0.5 up to 0.7 after a second of interaction. So, of course, this doesn't seem much, but that was the first time that quantum error correction was actually done. Since then, you can see that it took some time before in 2005 people realized a similar scheme than this one, actually, with photons. So they send a single photon, and so they had 2 photons. So they had a single photon that they use as a qubit, and they had another photon that they use as the Ancillar. And by doing Adama and then C0, and then some measurement depending on the parity check that they had, they could quantum error correct the original qubit. So that was in 2005. And then in 2004, so the year before, people have shown, so you can see it's a lot more complicated, but they've also shown quantum error correction with trapped ions. Okay. The problem with that is, so this, what it looks like is, so these green circles represent an ion. So they had 3 trapped ions, so trapped atoms. And what they had to do in order to correct, so one of them was the target, so one was the one that they wanted to keep the information, and the other 2 were ancillars. Okay. And what you can see here is that, so these orange blocks here represents electrodes. Okay, so with these electrodes, they can manipulate the atoms, so they can bring them together, or take one away from the other 2, and so on and so forth. So by this, so all of this scheme here, very complicated scheme, where you can see a series of Y and X and Z and C0 and etc. So something that would look like this. They could, and how they did that? They did that by shoveling the ions, so from this trap to this trap, and then they would remove, let these 2 interact, and then bring them back together, and then maybe this one would interact, and then the series would continue. So they would bring the ions close to each other, so one with the other one with the other one, in order to realize these C0 conditionally on 1 and 2 and 1 and 3 and so on. So what I'm trying to show you here is that, so that was quite some time ago, and yet it was just to quantum error correct 1 qubit using trapped ions. Okay, and trapped ions, there's actually a company now in the US called IonQ, I already mentioned it, that wants to sell a quantum computer made of trapped ions, but you can see how difficult it is and how still challenging it is to be able to implement quantum computing with quantum error correction. But nevertheless, it's still possible. It's still a lot more than what we could do before, but it also brings the idea of what I mentioned some time ago, is these non-perfect quantum computers. So how we can, so we know there are mistakes, we know we can correct them, but we know this is at a huge cost. So maybe perhaps we can work with noisy quantum computers and see what we can do. Okay, so this is the VQE, or the inertial methods I talked about briefly the other day. And that, I believe, you will see a bit more with the colleague from Atos, who's going to show you how we can say, okay, fine, we have noisy quantum computers, we cannot really correct them because at this stage, because it's too costly. So let's see how yet they can still help us to implement algorithm faster than a classical computer. Okay. So, so if I go back to quickly the planning. So we're done for today. So this lecture 12. As I said, there are 2 more. So next week will be someone from Atos on this quantum learning machine. So it's a machine that they sell. It's actually a computer, a classical computer, but optimized to mimic a quantum computer. Okay. And then the last lecture in 2 weeks' time will be given by a colleague from Spain who is going to talk more about the physics of the technologies, as I said, talking about superconducting qubits and trapped ion qubits, which are probably the 2 most advanced systems right now. Photon qubits and the electron qubits are good, but they are at this stage a bit behind in the race to build a quantum computer. So with this, I will stop here, and I thank you for your attention.